Join. Okay. Hi, everyone. I need the sharing.
Yeah, you do have the sharing.
Okay. Hi, everyone. Okay. Last time we talked about the multi regression, and we saw how we use the neural network as a simple one to do it. And we gave it as an example. We used the economics. Let me review that a little bit, and then we'll continue with the session today. Just one word about what we're going to do today. Today is really, I would consider it as the first example of real AI from A to Z. Okay? And, but number 11, there are a lot of concepts that we'll talk about today. And but before I dive into that, we'll spend at least one or two sessions on this one. Then we'll move to do similar things on recognizing some other things. Very similar methodology to do other studies in AI. At Turning Point, we already have covered a lot of concepts, but today really will be a classical AI session. But before that, let me just review a little bit what we did last time. Let's just talk from the very beginning. We talked about a short path. If you remember the very, very beginning, this was a classical dynamic AI, but we really didn't use any neural network. We just saw as a dynamic process that you study. If you study mechanics or something like that, you learn method like that with control. We learned a little bit about agent and environment. And I said, as we dive later on, we'll come back to that concept, but we'll augment it with the neural network. So we started with a simple case of agent, environment, how you behave as a response to the environment. And here we used it from this point to this point. So we click here, and I went over that, but we really didn't use AI in the conventional way. We used a dynamic programming, I should call it, okay? We will see in the future how we add what we're learning now on neural network to make this one to be a really sophisticated system. This will be a nice exercise. I really strongly recommend go learn the concept, agent, environment, action, a Bellman equation I talked about a little bit, and all of that. You'll see we'll come back to all of those, but we'll augment it with AI, and specifically neural networks. Now, from there, we kind of sidetracked, looks like we did, but we really didn't. We start talking about regression. And we started with the simple case of regression with one coefficient. Okay, like this one, we have the alpha and beta, or A and B. The slope was the B, and A was the constant. So if you have a straight line, let me make a simple one so you can really just, let's make it 10, and let's make it a positive, look more familiar to people, and they're more 0.7. Okay, if you have a straight line starting from 10, going with a slope of 0.7, it's like going up a line. What we did, we said, how about if we take points that generated by this one? What I meant by, if you remember when we did it, that generates some dot around that line. So here we get a sample of dots. They're going like kind of, but they're not really on a straight line. Then we said, let's assume you had this one. If you had that one, can you go kind of backward, find the original line that you created those dots? And we went over the mechanism, how we generated those points, okay? But this is just for real understanding. In real life, you really don't know that one. You can't really generate it yourself. You just see that and you say, well, what would be the line that can be as close as to those points? And the reason I gave that example, in order for you to learn some concept of like minimizing a distance, you know, we can say, okay, we want to draw a line here that will be as close as possible to all those dots. So we can assume, let's say, you know what I will do? I'll just like a simple line, okay? I'll run it. Hold a second, I will do it from scratch. So the line will not be exactly as nice. Okay, if you look at the, let me run it again. Well, no, cancel, do it, and no. What is another 100? That would be nice to me, I hope. There we go, it still doesn't like me. Let me refresh it. Let me make more, let me make 1,000. Should do it. Yeah, here we go. I ran it on that one. I didn't want to do that. Let me make a different one. Okay. The one we just did before, I'll take the minus here. You can play with it. It's a good one to play with. So on that one again. Okay. You can tell the first ones is, this line is not perfectly, okay, you can tell that the estimated A, it's only 5.62, while in real life is really supposed to be 10. This one is quite close, okay? But I would like it even to be closer. And then we said, how would the mechanism work? I'm just the first, you know what, I will start it all over. I just really want to, so you can feel comfortable. I'll run it with 200. I think I'm making it jumping every 200. Let me just, let me do 200. Let's make it from the beginning. Yeah, here we go. I wanted to start. You know, when you're starting, you're getting all those dots, and you start the process of learning, you really don't know. So you're just drawing a line, okay, randomly kind of, okay? And this line is not really as close enough. We can make it better. And what we do is we measure how far are those points from the straight line. You know, we can say, well, this one is really almost right on there. We can take another point. Let's say this one is quite far, okay? We take that distance and we square it. The reason we square it because those dots, they might be positive here, but this one would be negative. So we don't really care if it's on the right or on the left. That's why we put it square, so it doesn't matter if it was on the left or on the right, it will all will be positive and negative. We turn them to positive because we only care about the distance. So we take the distances multiplied by itself, we're getting all numbers will be positive. Now that number would go down as close as that line will be to those points. And we said there's this algorithm, and I'm going to talk about it more today. Okay, we finally get there. How it really does it, we'll go and talk about it a little bit. But the bottom line is, as I train the algorithm here, if I run it again, okay, it will get even better. It will get closer and closer. Oh, here, you screwed up altogether. You could do it, by the way. But if I do 1,000, you will see it will get better. It can do it. It can happen. But as time, if you give it more here, you'll get better and better. Run it again. Will get better and better as I train it. This process I will cover more in the next sessions, today and next time and in the future, okay? Let me make continue. Let's do another one. Okay, let's give it another one. Here we go. It's getting closer and closer. You can tell you know, it's 4.3. It should really get closer to 10. This one should be closer to 0.7. Let's try it one more. There's a halter. Here we go. It's getting better. You see, this is going higher, meaning the line is starting a little bit higher, and the slope is getting closer to the 0.7. Here is 0.71. Let's try it one more. Okay, and we'll learn about that process. It's a very beautiful process that, here we go. It's really getting closer. You can see the 0.7. And that's a whole topic. When should I stop? Okay, how many times should I run it? How many epochs should I have? And that's a whole topic that we're going to cover in the next several sessions. Okay, but for now, that was the first time we actually learn about there is a process. We're taking the distance from the line, we call it a loss function. And then we see when we change those parameters, how that the total of those distances getting smaller and smaller. And that's really what we see here. In the beginning, it was very high, and then it goes down. It's already getting to zero, of course. Okay. But really getting close. You can tell here 342, and getting quite stabilizing because this is really what it is. It's really getting almost to the original one. Okay, then from this one we said, okay, for this one we have the y depends only on one variable. Can we talk about the same things when the y depends on several parameters, not only on the x? And we said, okay, let's take an example of economics example. And we said, can we explain the link between export, education, high-tech education, how that affect on the GDP of a country? So a GDP of a country depends on several variables. And that's really getting closer to what we have here in the picture, okay? And we said the way it works is if here we have only one parameter, the 0.7, the coefficient, in here we'll have several variables. Every variable will have a coefficient. We'll multiply the coefficient by that variable. We add them up. We're trying to see how close it gets to the GDP. Here we're checking how close is the actual GDP to that formula. I think we went over that a little bit, okay, several times in the past. And then we said, okay, let's do it. And I went over the whole process. We downloaded data from the World Bank data. Let me do, I think I added Uganda here. Let's go back to Uganda, okay? And then we said, okay, well, let's train the model. When I run it, it's training the model and it's finding those coefficients. Here we had only one coefficient. Here we have several coefficients. Okay. This is only, if I do 50, that it still really doesn't really train it very well. So let me make a little, let's make 2000. Let's run it. It'll take a couple seconds. So it will do it quickly. Here we go. It finished. Here we have two of them, and I will come back to this example. In fact, we'll go over that. What the meaning of this one and this one. Let's just deal with only one of them. The blue one, the loss or the training. Last time I talked about that there's two of them, but let's just focus on the training for now. You see it's going down as you train the model. What does it mean to train? It really is getting those parameters. The parameters in this example, this is the coefficient, the intercept, and those were the coefficient that explain how export really relate to the GDP in Uganda. It's very important. You know, the export really is one good measure of the GDP. You look at education, not really much. And really, most of the countries, the general education is not what really explain the GDP. Okay, has a small amount, it's 0.04. It's kind of 4%. Okay, on the other hand, export has almost 70%. You can tell. Natural resources is very important in Uganda. Expand the GDP. And when we look at the high tech, okay, it has a higher than the general education, which makes sense. Still, it's not really that high. So if I wanted to summarize on Uganda, we use actual data, which we downloaded from the World Bank. We ran the same work that you study in statistic courses on regression. But here, you don't really have to make any assumption about the normal distribution and all those assumptions that you have to make in neural network. Almost there's no assumptions about the distribution of the underlying data. And that's the beauty, okay? Now, what we did here, we extended this simple example that has only one slope to a multi-variable, meaning multi in the sense that we have 1, 2, 3, 4 variables explaining the GDP. And if I want to make it as a picture, we have here the GDP, and we have 4 variables explaining the GDP. I skipped about activation function. We're going to talk about it now. We'll get to that in today and next time. And the only things we did here is after we multiply the coefficients by the variables, we added them up. We added the intercept. This is the intercept, which is really the 0.114 in this example. We add them all up. We try to explain the GDP. Very simple. Regression, which you study on a network, okay? Now, what I would like to do is extend it, okay? Don't get scared, okay? We'll go over it several times. It's a jump today, but I will go slowly, okay? We're gonna talk about the next example, real life example. You know, when you go, you probably have seen those kind of, you might have that at home or you're in school. You're writing, let's say you're writing on a pad, and then the computer take your handwriting and kind of as if you typed it yourself, okay? And here is an example. Let's say you're writing numbers on a pad. Let's say you write the number 5, and you want it to convert it to a typed 5. How the computer does it, okay? Or you write a 0, okay? You want him to convert it to a nicely 0, like as if you type on a keyboard, okay? So the exercise here, we want to take handwritten numbers and tell the computer, turn those one to a typing. And how do you do that? That's the challenge. I will just summarize several concepts we're going to cover. There's a lot of them. This is really, I would say this is the first session that we actually, real life AI, this is a classical session in AI that when you take a course in a good school, they will go over it. We'll do even better than that in the sense that we not only cover the whole concepts, we also will see how it actually works on Python, how we do the interface here on JavaScript. And you know, you're using Academy City, you can go home and you see this screen, right, working beautifully. So it's really A to Z, the whole process, okay? But there's several concepts you need to familiarize yourself. One, how do we present this is like, look, a picture that has somebody have written. So how do we present a picture, okay? And then specifically, we'll say how we present those kind of numbers for the computer to read it. That's concept number 1. Concept number 2, we will talk about neural network, not the one that we looked at the last time, that we have only 4 nodes. We call those nodes or 4 variables, but it could be many variables. In this case, we will use the one that will have 784, and I will explain how I got to that number as we continue, okay? So we will have a neural network that will have a lot of variables. not only for it. That, you know, in a regression, you get lost. You can't really do it with regression. This exercise you cannot do with the regression you study in statistical classes, okay? That's one. Second, we're not going to use only one layer. We're going to use several layers. So this is not only multi-variables, it's a multi-layer neural network. That's another thing we're going to cover in this module 11, multi-layer neural network, okay, implemented to identify numbers. That's a second one we will talk about. As we go, we will dive first time, how do we actually modify and how do we train the model? I will talk about a gradient descendant concept. We'll use a simple one. The truth of the matter, this one is like a quadratic equation, but we'll dive into that concept. And that's really will be a beautiful thing for you guys to actually understand how the computer does it. I'm not going to dive too much, or really you get lost, and I don't want to get lost. But it really would be important. You get the concept, and take my word for it. As you understand it in the future, even when you do very complex examples, you will really understand what it does without having to dive to the mathematics too much. I will spend only on this simple one, and then I will leave for the future when we talk about more complex. I won't get into diving into it too much. At least you will understand the process, and that's really the most important things. Okay. Then we will talk about activation function, something I mentioned before. Here we have an example. By the way, this is known as a sigmoid activation function. And I told you in this example, we didn't really use sigmoid. We use only in linear. But I will go and talk about it. I will explain a little bit why. By the way, this is used to be like, people used up to about less than 10 years. People used only sigmoid, and now everybody uses what is called ReLU function. And I will talk about it a little bit and the importance of it and how that relates to the gradient descendant, why people change their mind in the future and make it work really much better by changing that activation function. So those are basic stuff. I put here a link to whoever wants, you know, those are really nice. You know, start getting used to what, that's just advertisements. Hold a second. This is a nice one. They really explain it in a very simple way. I really recommend look at that one. There's another one here, a little, in my opinion, this is a little more kind of more professional, I would even call it. To look at it, it talks about the derivative and what gradient is. It's really nice. Look at it. Don't get scared. Get used to it. Okay? And take my word for it. Honest to God, I'm dealing with this book. Okay? This book is all mathematics. But since I'm also a mathematician myself, okay, you really don't need as to be an AI person. When you understand how the code works, you don't need to really dive into it too much, but it would be nice for you to understand those concepts, okay? So that's why I'm not going to derive all those functions for you. You'll get lost, okay? And I will tell you, go and study and master in mathematics at least and come back. You don't really need to do that, honestly. Otherwise, I will tell you, okay? You don't. I need to do that because I really dive into it deeply. But the beauty here, when you understand it, this is very nice blog that it really talks about several concepts. Go, get used to it a little bit. Don't dive too much. It's a very simple example. It looks hard. It is hard, okay, for somebody just beginning. But don't give up, okay? Go over it 1, 2, 3 times, and then eventually you'll understand it. And then eventually you will know that you don't need to dive into the mathematics to understand those concepts, okay? So let's start. So those 2 links that you have down there, and let's go back to here. I want to start today, first of all, to understand what does it mean, a picture, okay? So I'm going to run this, I will run just here so you can, I will run it on my computer. Here we go. I run it on my computer so I can show you. This one I cannot really show you the way it works on Python because the Python is on the server, but it's the same code. Okay, I usually develop it first on my computer and then upload it to the server. Okay, so let's start it. And I'll just take a sample. Okay, I take an image. Okay, it's putting randomly a number. Okay. It gave me a 0. I want a different number. I'll get back to the 0. Here we go, number 6, okay? How is this really the computer? How do we tell a pictures to a computer? A computer view a 6 the following. Look at this one, okay? Make it smaller, and then I'll make it bigger, okay? See, this is the number 6 for the computer. It has 28 columns on 28. You can have, by the way, when you buy a TV and they tell you this computer, this TV has a resolution of a 1,000 on 1,000, it means you have 1,000 columns on 1,000 rows. If you have a high HD, 4K, it means you have 4,000 on 4,000 for one picture. But this one is a simple picture, has only 28 columns or 28 rows. And pay attention here in here, it really is have, wherever it's black, it get a number 0. And whenever it's totally white, it will get 255. Let me make it bigger now a little bit. By the way, I made you a picture here on Excel. Let me open it. I put there a picture for you so you can see it. For example, here we have the number 5. Let me just click on it. I just took it really from putting it on the Excel. Okay, here is number 5. How does it do it? It really is 28 columns on 28 rows. And you notice wherever it's 0, it's totally black. And when it's 255, which is, numbers usually in pictures, it goes from 0 to 255. If it's a black and white, you have only one layer. If you have colored, you will have 3 layers with RGB, if you know those ones that combine them, blue, green, and yellow. And then you combine those and it makes colors, okay? But in any layer, it goes from 0 to 255. You can tell that here, I didn't get any 255, but it's close enough, 253. You can tell that this one is totally white around here. So this really looks like 5, but the truth of the matter, it's like a little square. Each one has a number. And for the eye, you can't really distinguish, so it looks like a number, like handwriting. You can tell here it's not exactly smooth. That's why people are making more columns and rows, so it's much smoother. But for our purpose, if you take a picture like that and convert it, when you write by hand, even you convert it to 28 by 28, the computer can recognize it. It's good enough for that exercise. So concept number 1, a picture for a computer. It really is an array. It's an array that has columns and rows. And in the array, we're putting numbers. When 0, it's totally black, and 255, it's totally white. And a gray color is some number in between. So if I see here like 130, like the edges, you see the edges that are smaller number. It's not 0, but it's not 255. And that's really when you have the edges here. When you see here the edges, they are kind of gray, you can tell. Okay, so concept number 1, a picture, it's an array. We can get that array, put it in NumPy array. Okay, and that NumPy array, we start playing with it as we'll see in a minute. Okay, so a picture is a 2-dimension array. That's really what it is, concept number 1. Okay, now if you look at the picture here in the neural network, we really don't enter the array, we don't really study from an array. We give it like a vector. When we give it, here is a vector, here is 784. If you remember in regression, we give it an array of 4 numbers every time. You know, for every year for the country, we give it 4 numbers. It's a vector. It's not a 2-dimension array. And that's point number 1. So how do we deal with it? When we have a picture is 2-dimension. How do we convert a picture from a 2-dimension to 1-dimension? That's because I didn't say it in the beginning, but that's another trick. It's really more a trick. How do we do that? Now, be sure that the algorithm we're using now, it's a neural network, or what is known as is really relatively simple neural network. We will talk about convolution neural network. We have an example here. Using convolution, here we go. We'll do the same exercise as we did there. I think I didn't even do it for you. I wanted to give it to you as an exercise in the future. If we need it, we do it together, okay? But in that case, in this example, as we will see in the future, we don't convert the 2-dimension array into 1. We actually use the data as a 2-dimension array. And there's an algorithm, believe it or not, that knows how to read a picture or 2-dimension and work on it. And that's a different concept, and we get and dive into it. It's very complex, by the way, so don't kill yourself if you feel, don't feel stupid, you are not. Take my word. When I studied it first time, honestly, I went over it so many times until I finally mastered it. So don't feel confused, go over it over and over, and then eventually it will make sense to you, okay? Take my word for it. That's really the way it works. What we want to do now, we're going to use a relatively, still complex, simple algorithm in taking 2-dimension array and converting it to 1-dimension. How do we do that? We simply, let me go and open this one. The way we do it, we take the first row, you see row number 0, you know, in NumPy 0, it's the first one. It goes up to 278. It's really 28. 27 is the 28th. It's always in NumPy and Pandas. The index starts from a 0. I won't get into that. There's a good reason for it. But what you can do is take the first row and put it aside. Take the second one. You know what? Let me open the Excel and I will show it to you. It's worth it. Okay? Let me open it. You know, I took it really the way I prepared it for you. You can take the first one, okay? Copy it. You put it here, okay? You take the second one, the second row, add it next to it, okay? As a continuation. Okay, you take the third one and you continue that way. You take the third one, okay? All the beginning, they are all zeros, but it's only for this number. Some other numbers, maybe somebody wrote it from the very top, okay? And that's why you continue taking every row in this picture and making one long row. So, you know, if you have 28 rows on 28 columns, you'll end up with one long row with 784. It's simply 28 rows times 28 columns. You will end up with 784. So this 784 that I put there, it's not coincident because those images from 2 dimensions of 28 by 28, they are being converted to one row. This one would be converted to one long row of 784 numbers. Now, what we're going to do, we're going to use 784, okay, as our vector to the neural network. Okay, so that's concept number 2. Take the picture, convert it from 2 dimension to 1 dimension. Now, by the way, now the exercise is very similar to the one we had in the regression. It looks like some of you might get confused and said, well, I don't understand what the connections. Think about Uganda. In the data of Uganda, we have data, okay? We have data for countries, I think from 1980 up to 2023. Every year we have 4 numbers, okay? 4 numbers for every year. So every year we're putting here the 4 numbers for Uganda, and we're trying to find out the GDP. What we're trying to do here in this example, for this example, we take 784 numbers representing the actual numbers here, okay? All those little numbers, the one that are written inside. We're putting all those numbers, we're trying to predict what is really, that this is really 5. It's like in Uganda from the export, the education, natural resources, we're trying to predict the GDP. Here, from those numbers representing this picture, we're trying to predict that this is number 5. Okay, for this one would be the number 0 and etc. So now let's think about it. Okay, and we're putting all those numbers, 784 numbers, we're trying to predict that number. Now, this one slightly, it's it's a little harder than the GDP example, the economics example. Why? In the GDP, the only things we try to predict is the GDP. It's one number. Okay? The numbers could be high and low here, and that's why the reason it's called regression. It's regression because we're trying to predict a specific number. Okay, so the GDP will be 10 billion or something like that, 11 billion, 15 billion. In this example, okay, we are putting all those numbers, we're trying to predict to which category this image belongs. I'm a little confusing maybe, but I will explain that again. We're trying to say, okay, based on all those numbers that representing this image, which image is it? Now, those images can belong to one of 10 possibilities, 0, 1, 2, 3, up to 9. So my guess, what I'm trying to do here in this example, I'm putting all the representations of a specific image in here, and I'm trying to predict to which category this image belongs to. Okay, there is no specific, I'm not trying to, it will say number 5 here, but it really number 5 in here, it really is a category. Why? There could be other examples. Let's see if I can find another 5 here. And that's 6. Let's see if we get, okay, let's get more images. Let's say this is 8. Let's see if we can get other one. Here we go, another 6. It's not the same 6. Okay, might look a little bit, but this is like number 3. There could be several numbers. This is number 0. There's many, let's say number 2. A lot of handwriting of number 2 could be very different. Our objective when we predict number 2, we're really saying all those images belong to category number 2. That's why we predict there are 2. But we are not predicting a number 2. I hope that's clear. It's already easy concept. And therefore, in this example, although we're predicting which number it belongs, okay, we're predicting to which category it is. Maybe I will skip. I will jump to another example we're going to view. Let me see where I put it. It's another beautiful example. Is that here? Yeah. Okay, we use here convolution, but I will explain. This is another example. We'll talk about it in the future, but the concept is very similar. In this example, we're trying to predict the handwriting, which number are we really writing? So let's say this one belongs to the category number 5. Here we will try to see, we'll take pictures of clothes, okay? You see the beauty. We're covering this example, we'll see a lot of other examples that falling on it. Here we go, we have a shirt here, okay? It's a top shirt. We can have a lot of top shirts. We take seven, by the way, I can maybe make it even more examples so you can see it. I put 4, so you'll have more examples. Here we go. There could be many kind of there. All of those falling under the category of top shirts, okay? This one is for dresses. And believe it or not, those images being presented very similar to the handwriting. It will be 28 by 28 pictures. In this exercise, we will try to predict each image to which kind of dress it is. Is it a top? Is it a trouser? Is it a pullover? Whatever. The exercise is really almost one-to-one to the one we're doing with the numbers. The only things here, I will use convolution. It's another type of an algorithm. We'll get there. But the question is very similar. I have pictures. In this case is pictures of clothing. Can I categorize that picture to which kind of clothing it belongs to? Okay, all those 4 belongs to the top. These 4 belong to type of sandals. Those 1 to bags. Okay, the beauty, the concept is very similar. Just here we use a simple algorithm. And you, by the way, you can apply the most sophisticated algorithm to those ones. You even get better results because every algorithm might make a mistake. This one is quite good, by the way. It's almost 98 point something reliability. So it's very, very good. But this is still a simple neural network, multi-layer neural network, but it's not convolution. Convolution is very complex. We're getting to that, but it does beautiful results. It's very getting close to 100% accuracy, which is amazing. When we talk about computer visions, it's all using convolutions, okay? But it's really good to understand the whole process, a lot of concepts by starting with a classical neural network example, okay? So anyway, what we're trying to do now here, it's really, you will see in the end, that's why you don't see only one node, you will see 10 nodes in the end. It means you have 10 categories. And you will see we're going to other more technical concepts as we're going along, okay? But here, this problem is categorical problem versus regression. In regression, we have several input. We're trying to estimate a specific number. Here, we're trying to estimate to which category an image belongs to, okay? Concept number 3, okay? Okay, in this example, we're using neural network, in fact, to categorize images to which category that belongs to. Another concept that I'm going to, I said this one is a multi-layer. Why is it a multi-layer? We have not only one layer as we have in here, and then from this one layer, it goes all the way right directly to estimate the number. Here we go into several layers. This is really hard, okay? Don't get lost, okay? I'm gonna say it. I'll go over it several times. And let me start first by this example. If you notice this one, we said, we take, let's say, the data for Uganda for, let's say, the first year, 1980. We take the export, we multiply by coefficient. We take the education, multiply by another coefficient. We take the natural resources, multiply by another coefficient. And we do the same for the high-tech education. After we multiply each one of them, we sum them up. We add to it some number that they intercept, and we get our estimate to the GDP. In fact, if you look at it as a vector multiplication, let me give it a try. I hope you guys know vector multiplication. I will go over it quickly. I'm not going to teach it, okay? It's like you need to take several courses but I would just give at least that simple one so you can understand. If I have two vectors, let's say I'll just make numbers here. I just make simple numbers. Okay, I have 4 numbers. This is a vector. This is laying down vector. And I want to multiply it by another vector of 4 numbers. Let me just put this vector would be 1, 2, 3, and 4. I'm just making it up. It doesn't really matter. Okay. You know what? Let's make it simple. So we don't really, I'm not going to cover here to teach that, but let's just make this one so you really understand what a vector multiplication. Anybody doesn't know any mathematics of vector multiplication? Let me know. Don't be shy, guys. Don't be shy. Anybody never saw multiplication, vector multiplication, let me know. But I will cover it quickly, okay? I'll just do it quickly. Okay, how do we multiply this one, this vector by this vector? We simply take 1 times 1, 4 times 2, 5 times 1, and 6 times 2. And the way you can write it, you can do equal. And you will take this 1 and you multiply it by number 1 here. Then you add to it the number 4, multiply by the number 2. And you add to it the third one, number 5, times the 1. And you add to it number 6 times the 2. And then you get a number, okay? By the way, that's what we did with the GDP. We got the export, the education, the natural resources, the high-tech numbers, and we multiply them by the coefficients. You can look at those ones. So I can call this vector coefficients. Excuse me if I misspell. I usually have a problem in spelling. Okay, those are the coefficients. And by the way, for specific here, we take those numbers of the country, multiply them by the coefficient, we get the x. If we get a different year, we might have different numbers. We're multiplying them by those coefficients, we get the expo for the second year, etc., etc. Now, I want to move to multiplication, not of a one vector by the other one. I want to take a vector and multiply that vector by a matrix. Okay, a matrix. Okay, by the way, in this example, if you really want to follow, we will need, you know, when we're taking those data, we're getting 784 numbers. We want to convert them to 512. That's quite a matrix, by the way. It's a huge matrix, but we don't really care. The computer does it. Okay, but I'm not going to use this example. I'm going to use a simpler one. I'm going to use that I will have, I'm going to take those 4 and make even 5, just to make it different than the previous example. Okay. I have a vector of 5 numbers, and I want to convert it to a vector of, let's make 6. You know, make it 3 so you don't really get confused. Okay, I'm going to take, we'll have, let's make those numbers 1, 2, 3, 4, 5, and I want to convert it. So after I multiply it by the matrix, I will get a vector with only 3, okay? So I will need a matrix with, first of all, since I have 5 here, I will have to have 5 rows. And I want to convert it to 3, I will need to have a matrix of 5 by 3. So let's color it by different color. Okay. I don't want that one. I will take a different color. So let's see there. I don't know why it doesn't like me. It's okay. I'll put the numbers there. Okay. So 1, 2. So let's fill it up. We'll have, let's just put some numbers here. Okay. I'm just writing some stupid numbers. Okay, but we have 5 here, we have 5 here. Okay, what will happen when we do that this way? When we take a vector and that has 6 number, multiplying it by a 5 number, sorry, multiply it by a matrix of 5 by 3. You can tell immediately you will get a matrix, you will get a vector with 3 numbers, which makes sense. Okay, let's start with the first one. Okay, let's start with the first one. Okay, how do we do the first one? We just take this one and we multiply it by this one. Okay, we keep doing it. The second one, multiply it by the second one, and etc. I hope you're getting the idea. Okay, we got the first one. Now, if I can really copy it, it will be, all right, that's for the first one. Okay, you know, if I copy it to here, it won't work. Well, if I really want it to work, I will have to do here F4. I do it this way. And I might be able to copy it and will do the whole work for me. Okay, and I'll just copy it from here to all those 3. Here we go. So basically, the second one is taking this one, multiplying it by this column. And then the last one, the third one, really taking the same vector, multiplying by the third one. So this way, I took a vector of 6 numbers and turned it to 3 numbers. Now, this is a beautiful thing, by the way. By the way, you could have done, you know, you can take a vector of 3 converted to 6. How would you take a 3 converted to 6? You just make a matrix of 3 by 6. Okay, so a matrix is like a function. You can think about multiplying a vector by a matrix is like utilizing a function, which can convert a vector. This is called like the 6-dimension vector space, converting it to 3. Why do we want to do that, by the way? What's the idea? The idea is that this matrix can take the information in here and shrink it. By the way, a lot of algorithms of compression works on using compression by using matrices. If this matrix converting it here to 3 number only, and that 3 number can represent the picture as if it was a long vector, good. And that's really what we're trying to do here. We're taking the image, which is 784 numbers, and we're trying to convert it to a smaller, it's still big, but it's smaller, to 512, okay? So we're trying to convert it to 512, and then, by the way, we take another layer, at the 512, we convert it to 256, and from 256, we're converting it to 128. By the way, if you have a good, if you already get used to, in computer, 2 power something, it's a very important duplications. So it's not coincident that we use 512 here, and we use 256. Pay attention, this is half of this one, and this is half of this one. And then eventually, by the way, some people would put 64 or put 32, but usually this works very nicely, by the way. And in fact, even in the algorithm I implemented, I didn't really use so many layers, even 2 were good enough. The final one had a 10, okay? And 110 because each one going to represent a different category. We'll talk about it a lot in the future, okay? But stage number 1, another concept we have learned today, if we have a vector, we can convert it to another vector with a smaller dimension, smaller vector, okay? And we can do it several times even in the process. why do we do it several layers? Why didn't we just convert this 784 right to the 10? That's a very good question. The truth of the matter is the more layers you have inside, it's make this as if we are making a function, non-linear function, and it's close to very smooth. What do I mean by that? When we did the regression, this is a straight line. You know, it's just like this example is a straight line. This is also a straight line. It's just 4 dimensions. We have 4 variables. But eventually, this is really a straight line. It doesn't really have a curve, okay? So you can't really, like, equation like this one, like a quadratic function like this, you cannot estimate by a straight line. It will be just straight line. It will be a bad estimator. If we want to get something, by the way, this could be a good exercise for you. I will talk about it more next time. I will just give a little brief today. I will talk about this one. I can give it to you as a good example. I'll give you just that they are quadratic, and let's see if you can estimate it using neural network. And you will see neural network, although it seems like all linear, it's only coefficient, it's very close. You can really estimate even non-linear functions. If you study statistics of regression and you try to estimate non-linear regression, it's a very complex task in regression, and there are not really good ones, okay? And you're compromising. The beauty about neural network, using this trick of having several layers, okay, and then estimating something which doesn't have to be linear, neural network is beautiful. This is why neural network is so powerful and used in AI. Okay, so there's several concepts we have learned today. Stage number 1, concept number 1, image is being represented by an array, 2-dimensional array, or 3-dimensional array if it's a colored. In a colored, we don't have only 1 Excel, we'll have 3 Excel for each color. All those 3 together, we will look at that in the future, okay? How do we deal with colors once, okay? But for now, we're just dealing with black and white, and we have gray, of course, and we have only 1 matrix. So image is being represented by a matrix of 2 dimensions. To use it, we convert that one to a 1 long vector. We're taking every row and we add them up one after the other one, and we get 1 long array, okay? That one, we're going to estimate by converting this one into a smaller, up to a point we're getting to only 10 numbers vector. And each one of those lines, one of them going to represent which category it is. So the first one could be representing number 0. The second one, the number 1, etc., up to number 9, which will represent the number 9. Yeah, 0 up to 9 will be representing number 9. So, and then we'll see, how do we do that? That's another concept which we talk about, and how do we convert them? We will utilize, okay, a little more sophisticated the sigmoid, okay, but we put on that another layer of sigmoid, which calls softmax, and I will explain that next time. Okay, but for now we did really good. I hope you really understood that one. All that one. How do we get to that point? Next time, we'll talk about this the layers, the activation function. And when we're converting from here to here, we convert those numbers. We do one more things. We don't just take the numbers as they are and leave them here. We implement another function that's called the activation function. And then finally, in the last one, we don't just use a simple activation. We use it, especially in categorical one, we will use what is known as a softmax activation function. Beautiful concept. It's a little hard, but it's a beautiful concept. Eventually, based on that, we can say, well, this picture is showing me that this one is 1, getting 1. You will see next time how that function works. If this one becomes to be 1, let's say the number 5, becomes to be 1 and all the rest will be 0, then I said this category is 5. We'll do it next time. Second, we'll do next time also. How do we determine those coefficients? We'll go back a little bit to this example. Okay, we talk about not a straight line, we talk about quadratic one, we talk about this function, and I will show you how the algorithm try to estimate those coefficients and how it works. We talk about derivative. I will go slowly, I won't go too fast. Okay, if we need, we'll add another session for this one. But this is beautiful concept that you will see they will repeat themselves as we go along. All those concepts will repeat themselves and then you get used to it and you won't get scared anymore, okay? After we learn this one, I will explain how it's being applied to this complex relative to this simple example, this one, how this one, and then we conclude by going to the code itself in Python. Okay, we'll go over this Python code and we'll give you to play with it, okay? And then you can go home and play with it. Fair enough? Any questions, guys? Don't be shy. It's not easy stuff, but it's a good foundation. And if you made it so far, you probably can handle it, okay? It will get hard, but then it will start getting easier because we'll repeat those concepts, and those stuff will start making sense to you. Questions, guys? Yeah, I want to hear some questions. Don't be shy, guys. I have a million questions, honestly.
Mine
Go
is
ahead,
just
guys.
a,
Anybody?
mine is just a comment.
Yeah?
Yeah, I think I understood today's session, and maybe if what I picked out was the multi-layer neural network basically means you'd actually have to have knowledge on vectors, right? As I understood it.
Correct. You know, if you look from this layer to this layer, you would have a matrix of 784 by 512, which will do is if you have a matrix, this matrix that I made is 5 by 3, it will just have a very 784 huge matrix, and we'll have 512. And then if you have a vector of 784, and here I made only 6, 784 multiplied by 784 will give you one number. But you keep doing it, okay, 512 times. So this one would be 512 times. This will be only after this layer. And then you do it again on another matrix. The second matrix will have 512 by 256. This is really, it depends. Here in this picture, we use 256. I think I use only 64, the actual one. So after you get a vector of 512, you can convert it to 256 by multiplying it by a second matrix. And that matrix will be smaller. It will be only 512 by 256. And then whatever you get, the vector you get, you multiply it again by a third matrix, which will have 256 by 128. That's the one here. Finally, the last one, when you get a vector of 186, you multiply it by the last matrix, which will have 228 by 10. And then the last vector will end up to have only 10 numbers. Okay, so this process of multiplying by several matrices, taking a vector of 284 and convert it eventually to only a small vector of 10. And the beauty is, and that really is the beauty of this method, that all the information that you have in 784 numbers ending up with only 10 numbers. Moreover, we will see that those numbers are not just numbers, they will end up to be only 0 or 1. The first one, if it's 0, it will be the first one, will get 1. If the second one is the 1, this one would be 1 and all the rest will be 0, depending on the picture. But we'll go over that more in the next time. Okay, guys? That's a good question. Go ahead, guys. Good comment.
So
Don't be shy, guys.
does it also mean that when you're multiplying the vectors by the matrix, there is always a standard size, or it depends on what you're doing?
Exactly. Beautiful. You're right.
Varies.
If I'm defining the layers with 784, the matrix will be 784. The second one depends how many I'm defining in the second layer. If I define it's 256, so the matrix will be 784 by 256. Now, the second matrix will be 256 by the one I defined, the third one. If I define it to be 128, then it will be 256 by 128, etc. Up to the end one. The last one I can tell it's 128 by 10. And depends on how I define this one, by the way, there is no guideline tell you how you should define it. But there is a lot of experience that people have. This one will do beautiful work on this kind of a question. It might not do very good on clothing. That's why we use convolution. It will do okay. It will give you like 90, 92% good on clothes. Okay. But if you want to get a very high, this method will not be as good as another method, another structure. But this is a good one to so many problems. And for many, many problems, it's a very good one, by the way. Okay. So one more question, guys, I would like to hear, and then we break.
Doctor, maybe on top of what Brenda has asked, so I just wanted to also inquire whether you have to just come up with a random matrix values, or there's a value that you depend on, the matrix value.
Oh, I know this is a beautiful. In fact, in this example, we had only two coefficients, remember? And we said we don't know them. So the stage number one, let's do it again, okay? By the way, in this example, you have only two parameters that you don't know. Okay, let me make it similar. Okay. Why didn't like me? Yeah, of course. I may have put a big number here. Here we go. Okay, look at those dots. There is only two parameters. You're trying to draw a line. This one is a thousands times more complicated. Here you have a matrix. The first matrix is a huge one. Just do the multiplication. 784 by 256, you get 10,000 parameters. Only for the first layer. I don't really know those numbers. I'm going to estimate them. This is when we click on train here, we're telling the algorithm, go find those parameters. Exactly similar to the way we did it here. But this one's just a simple one. It has only two parameters. Here you have thousands of parameters. So this is a beautiful question. It really is. How do I find those numbers of those matrices? That's what we will do next time. Next time, I will start to explain how the algorithm does it by taking a simpler example of quadratic equation, which is already not simple, but it has only, this one, by the way, has only one parameter too. Okay, and I can make a complex functions with 3, 4, and then you already get lost. And the beauty of this is algorithm that he knows how to find it. Here is going to find thousands of parameters. But how does it do it? How does it know those numbers? And that's the beauty of next week. We'll talk about it next week. It's a beautiful, this is the heart of the AI. To understand what we're going to cover next time, it's called gradient descendant, this method. And it really is for mathematics. Okay, we'll learn how, it's like here, when you have a chart like this one, we talk about derivative. I will explain what it means. We'll do it slowly, and then we'll jump to this. I'm not going to dive into this one. This is really complex. It's a derivative of a vector of thousands of vector. But we don't really need to dive into it too much. But this concept will really shed light to the question you ask. Yeah, I like this question. Beautiful, beautiful. This is really is the heart of that. Okay, guys, thank you. And we see you next week, okay? Same time. Good luck and don't be shy. Contact